This is Calculus 12, Chapter 2.3, Part 1. Continuity. And the big idea here is if we can draw a function without lifting up our pen, then the function is continuous. However, with math, we need to show this using limits and theorems. And to show this, we'll need to know the definitions. A function f is continuous at an interior point of A of its domain if limit x approaches A, f of x equals f of A. So you're going to need to know what an interior point is, and we'll cover that in a minute. If f is not continuous at A, then we say f is discontinuous at A, and A is a point of discontinuity. A function f is continuous at a left point of its domain if the limit x approaches A from the right of f of x equals f of A. A function f is continuous at a right endpoint A of its domain if the limit x approaches A from the left. Okay, so this is important. Remember that we said the limit as x approaches A of f of x does not necessarily have to equal f of A. But if it does, then that means it's continuous. So here are the types of discontinuity. We saw this one before. This is called infinite discontinuity. So even though this one matches, it's still a discontinuous point because we have this situation. It's undefined at f of A. Here, we say this is point discontinuous. As well as this one. This one is slightly different. This one is called a jump discontinuity. Okay, so the left and right limits are equal, but it's not equal to the value here. And this left limit and right limit don't match, so we call this a jump discontinuity. And point discontinuities can be removable. And we can remove the discontinuity with a piecewise function. So here's an example. F of x is equal to x squared minus x minus 2 all over x minus 2, and remove the point discontinuity. And the discontinuity is at the NPV, so x equals 2. And we take the limit. X approaches 2. F of x, and we substitute. And we have to factor. And we simplify by canceling. And we still need to break up this limit. If you don't break up the limit, you'll lose marks. And this is just 2 plus 1, and it's 3. So now we still have to answer the question. And we have x squared minus x minus 2 over x minus 2 whenever x does not equal 2, and we simply say it's equal to 3 when x equals 2. If you plug this into your calculator, you get a better graph than I can draw. But you can see that it gets very tight in here because it's oscillating faster and faster as we get to 0. And it's not defined at 0 because we have 1 over x. And it just spreads out. The period gets longer as we go off towards infinity. This is called an oscillating discontinuity. Here's an exercise in your textbook, and let's go over some solutions. Note this particular point discontinuity is there. And we have a circle here and a dot there. So we answer this graphically. So you should be able to look at a graph and just say what the limits are. A, does f of 1 exist? And it does, so we should just answer the question. Yes. F of 1 is simply this. F of 1 equals 1. B, does limit as x approaches 1 of f of x exist? Yes. And it's here. Limit x approaches 1 of f of x equals 2. C, does the limit of x approaches 1 of f of x equal f of 1? Well, clearly no. We have 1 and 2. D, is f continuous at 1? No, it's point discontinuous. Now, if we're to solve this algebraically using the function definition, A, well, f of 1 just equals 1. B, we have to do the limit. Limit x approaches 1 from the left of 2x equals 2 times the limit x approaches 1 from the left of x. So this equals 2 times 1, and that's 2. Limit x approaches 1 from the right, negative 2x plus 4, and we have to split this up. 2 times the limit x approaches 1 of x, that's a negative, plus limit x approaches 1 of 4. So we get negative 2 times 1 plus 4, and that equals 2. And we have it so that limit x approaches 1 from the left, f of x equals limit x approaches 1 from the right, f of x. So limit x approaches 1, f of x equals 2. And C, well, our result from A does not equal our result from B. And D, we use C, therefore no. And that completes our lesson.